Okay, let's just dive right in. Welcome to today's explainer. We're going to do a deep, real engineer-focused teardown of one of the most ubiquitous, yet honestly, frequently misunderstood components sitting right there on your PC, the network connector. We're stacking up standard non-magnetic jacks against integrated connector modules, or ICMs. Because look, if you're designing hardware, you already know the deal. The choices you make right at the edge of your board, they can literally make or break your entire system's performance.
So I want you to think critically about your current design process for a second. Are you maybe over-engineering your network ports? Manually routing discrete components and just eating up valuable board space? Or, flip side, are you missing crucial internal circuitry because you're assuming a standard jack is, well, enough for high-speed data? Today, we're really going to challenge some assumptions about standard RJ45 ports. We'll see exactly how picking the right connector strategy drastically impacts both your signal integrity and, of course, your bill of materials.
Here's our quick blueprint for the explainer today. We're going to cover connector basic classification, then a non-magnetic jack analysis, followed by magnetic connector advantages, an internal circuitry teardown, and finally, an application scenario comparison.
All right, let's kick things off with Section 1, Connector Basic Classification, Drawing the Line.
So the real jumping off point here is the fundamental divide in modular jack design. On one side, you've got your standard modular jacks. Think of these as purely passive physical connections. They're basically just plastic housings with some metal pins, right? Absolutely no internal components whatsoever. But then on the other side of the fence, we have integrated connector modules, what we all know as ICMs. Now, these are active. They provide active signal conditioning right there at the port, and they've got built-in magnetics. So one is essentially just a physical bridge, while the other is a complete, fully baked electronic module packed into this incredibly tiny space.
Moving right along to Section 2, Non-Magnetic Jack Analysis, the Standard Foundation.
Just look at the sheer variety of physical form factors available for these standard jacks. When you look at the Vitalconn 30, 32, and 52 series, you see it all. Horizontal mounting, vertical, keyed, unkeyed, shielded, unshielded. Mechanically, incredibly versatile. But remember what we just talked about. Electrically, they are basically empty boxes. If you're going to drop one of these standard jacks on your board, every single piece of signal conditioning, I'm talking your isolation transformers, your filtering caps, your termination resistors, the whole shebang, has to be laid out manually as external discrete components on the PCB. And you know what that means? It requires incredibly meticulous layout routing just to maintain your signal integrity and dodge that dreaded EMI.
Which brings us to Section 3, Magnetic Connector Advantages, the all-in-one solution. Now, this blueprint for a multi-port 1x(n) series gigabit connector, it brilliantly illustrates the absolute magic of ICMs. By going with an integrated connector module, you're basically taking what would normally eat up massive chunks of your PCB real estate and ingeniously consolidating it into a single, compact, shielded housing. All those discrete components we were just worrying about laying out, yeah, they're already tucked away safely inside this metal shield.
Let's break this down into some hard engineering data. Look at the PCB space required here. Standard jacks with discrete components, they demand a large footprint. An ICM, on the other hand, requires minimal space. What about component sourcing? Well, the standard approach adds multiple line items to your bill of materials. You're sourcing the jack, the transformers, the resistors, the capacitors. It really adds up. But the ICM approach? It's a single part number, literally one line on your BOM. And then there's EMI shielding, which is absolutely crucial for compliance testing. With discrete components, your shielding is super variable. It depends entirely on how skilled your PCB layout engineer is. But with an ICM, that metallic housing securely shields all that internal circuitry by design right at the point of entry. It's built right in.
All right, time to get a little closer in Section 4, Internal Circuitry Teardown, X-raying the ICM.
Okay. Check out these complex blueprints pulled directly from the Vitalconn component catalogs. This really reveals what's hiding inside those magnetic jacks. And I want to be clear, this isn't your PCB layout. You are looking at highly sophisticated analog circuit design packaged directly inside the plastic and metal housing of the port itself. It's essentially an entire subsystem dedicated solely to cleaning and protecting your network signals before they even have a chance to hit your main board.
So let's demystify exactly what we were just looking at on those schematics. First up, you've got your 1CT to 1CT isolation transformers. These guys are absolutely vital for signal conditioning and making sure you have DC isolation between the outside cable and your PFY chip. Then notice those arrays of 75 ohm resistors. They're giving you precise impedance matching and common mode termination to just filter out all that noise. You'll also spot some pretty beefy high voltage capacitors in there, specifically 1000 picofarad 2 kilovolt caps paired up with 0.1 microfarad caps. Why? Because high voltage isolation is crucial. They create a safe grounding path that protects your expensive silicon from nasty power surges coming down the network cable. And finally, you have dedicated shielding connections tying the whole thing to chassis ground to just completely lock out EMI. Best part? All of this is pre-engineered, perfectly matched, and tested right there inside the ICM.
This leads us directly to Section 5, Application Scenario Comparison, Where to Deploy.
When we bridge the gap from the theoretical circuitry over to practical engineering deployment, the use cases become pretty clear. Look, if you're building standard consumer electronics, maybe some basic modems or simple telephones, places where data rates are pretty low and board space is, plentiful, then standard non-magnetic jacks are perfectly fine. They get the job done and they're cost-effective. But for demanding, high data rate environments, ICMs are essentially non-negotiable. We're talking 5G wireless infrastructure, industrial IoT platforms, big enterprise servers, and even super-sensitive medical equipment like mass spectrometers. In these kinds of environments, having that pre-engineered internal filtering, the high-voltage isolation, and that superior EMI shielding built into an ICM, it's not just nice to have, it's absolutely critical for passing compliance and guaranteeing reliable gigabit or multi-gigabit data transfer.
Which really brings us to the ultimate question for you, the designer. Based on everything we've covered today, from streamlining your BOM to digging into those internal transformer schematics, what's your next move? In your next PCB layout, are you going to choose to save space and instantly boost your signal integrity with an ICM? Or does your specific use case actually demand the complete, hands-on customization of laying out discrete non-magnetic components yourself? It is a fundamental architectural choice. But hey, now you've got the blueprint to make the right call. Thanks so much for joining me on this explainer, and as always, keep engineering brilliant solutions.